So, Robert, you're saying writing clean code is hard, especially when you're dealing with multiple threads. Is that a common problem, or is it something only very specific experts have to deal with?
It's definitely a common problem. Writing clean, reliable code, especially when dealing with concurrent tasks, is a serious challenge for most programmers. The complexities go beyond just knowing the language, you know?
I see. So, what are some common mistakes that programmers make when they write concurrent code? What are the usual pitfalls?
Well, race conditions are a big one. Imagine two threads trying to access and modify the same shared resource without proper synchronization.
Oh, like a bank account being updated at the same time by multiple users?
Exactly. Or imagine two threads trying to grab the same lock, and one gets stuck waiting forever. That's a deadlock.
Wow, that sounds tricky.
And then there's the issue of ensuring the code is deterministic, which is very difficult in the context of concurrency.
So, how do you approach writing clean concurrent code? Any best practices?
Absolutely. Using locks, mutexes, and atomic operations can help. You need a very structured and methodical approach.
Is there a specific programming language that makes it easier to write concurrent code?
Some languages are more geared toward concurrency like Go, but even in languages like Java and Python, you need to understand the specific tools designed for threading.
So, how do you test concurrent code to make sure it works properly?
That's a real challenge. You need to simulate multiple threads interacting in a controlled way, and often have to consider edge cases and potential conflicts. That's why it's so crucial to test thoroughly. A lot of debugging can involve special tools and techniques.
That's a lot to keep track of. It seems like a significant amount of planning is necessary before you even start writing a line of code.
Absolutely, it's a significant investment up front, but writing clean, concurrent code significantly reduces the likelihood of errors later.
So, what would you say is the single most important takeaway from understanding concurrency?
Understanding the complexity and taking the time to plan carefully from the start. It's not about avoiding concurrency, but approaching it with the right mindset and tools.
Thanks, Robert. That was very insightful.
My pleasure. And remember, this is a deep topic. We'll delve further into this in concurrency too.
Great. I'm excited to learn more. So, Robert, you've just painted a compelling picture of concurrency. But, doesn't it sound like a major complication over simpler single-threaded approaches?
Well, Andrew, it's a trade-off. Single-threaded code is often easier to understand and debug, but as applications grow, they can bottleneck. Concurrency lets us handle multiple tasks concurrently, and this is often the key to scalability.
Okay, give me a concrete example. Like a real-world app where concurrency is absolutely critical.
Think of a web server. If it has to handle just one request at a time, it becomes incredibly slow with many users. Concurrency lets it process multiple requests simultaneously. That's why you see responsive websites.
Wow, that makes sense. So, how does this what and when decoupling work in practice?
Imagine a task involving many small steps. With single threading, you execute those steps one after another. With concurrency, you can potentially execute some steps in parallel, speeding things up considerably.
So, is this just a matter of having multiple threads?
Precisely. These threads work together on separate parts of the task, and then combine the results. But it gets tricky, coordinating these independent threads to avoid conflicts and ensuring everything works correctly takes some care.
That sounds tricky. What about debugging?
Debugging concurrent code is indeed more difficult than debugging single-threaded code. You need tools and techniques to track the interactions between threads and avoid race conditions. You also have to be aware of potential deadlocks, where threads get stuck waiting for each other.
Wow, so many new potential headaches. Is it worth the trouble?
Absolutely. The benefits in terms of performance and scalability often outweigh the added complexity. The right approach is to apply concurrency where it's critical, and use single-threaded approaches when simpler is sufficient.
That makes a lot more sense. I think I get the core idea now. Thanks for clarifying this for me, Robert.
My pleasure, Andrew. It's a fascinating field, and there's always more to learn.
Hey, Robert, we're diving into clean code today, and I'm really excited to hear your perspective. You know, I've seen code bases where concurrency is just everywhere.
Yeah, Andrew, it's a common pitfall. The single responsibility principle, or SRP, is key here. It's about keeping one part of your code focused on one thing.
So, what makes concurrency a separate thing?
Well, concurrency is inherently complex. Debugging race conditions, deadlocks, these problems have a unique set of challenges, separate from, say, user interface logic or data validation. Think of it like different gears in a machine.
So, you're saying the life cycle of developing concurrent code is different?
Precisely. It's about development, testing, and tuning. It's a separate beast, and should have its own dedicated section of code.
Okay, got it. But how do we practically separate it?
You create modules or classes that handle your concurrency concerns. It is really about not getting the application logic and concurrent logic mixed.
Like a dedicated concurrency class?
Exactly. And this applies to databases, network communication, etc. If you have lots of moving parts, you keep those parts isolated.
So you're saying that concurrency has its own unique challenges that should be isolated?
Exactly. Separate, maintainable, debuggable. That's the benefit of this.
That makes sense. Thanks, Robert. This really helps. Any real-world example?
In a high-frequency trading application, concurrency is paramount. If those threads aren't cleanly managed, the whole system can crash or have inconsistent data. Separation prevents that.
Wow, that's powerful. So, it's not just about tidiness. It's about reliability.
Exactly. Clean code makes everything better.
Thanks for explaining this. This is much clearer.
You got it.
Hey, Robert, concurrency is everywhere, right? How important is it to handle threads correctly in code?
Absolutely. Correct thread handling is critical. Improperly coded threads can lead to data corruption, deadlocks, or just slow performance. It's a real pain.
So, are there specific tools in Java 5 to help with this?
Yes. Java 5 introduced thread-safe collections. Think concurrent hash map, crucial when multiple threads access the same data.
Wait, what's the difference? Non-thread safe collections?
Those are fine for a single thread, but if multiple threads mess with it simultaneously, things go wrong. Imagine two people trying to edit the same document. Chaos.
Right. So, thread-safe collections are the fix. What about unrelated tasks?
The executor framework is your friend. It manages pools of worker threads, so you don't have to manage them yourself.
So, we hand off tasks and it takes care of the threads?
Exactly. Cleaner, more efficient, and less to worry about.
And non-blocking operations? What's up with that?
Non-blocking operations are great for avoiding delays. You avoid waiting for something to finish.
Are there downsides?
Sure, sometimes blocking is simpler. It depends on the specific task.
So when do you use blocking, and when do you not?
Use non-blocking when performance is critical. Blocking is simpler for less demanding tasks.
Good point. Thanks for this quick rundown. It's clearer now.
You're welcome. Happy coding.
I'm feeling more confident about handling threads now. Thanks, Robert. So, Robert, we were just talking about multi-threading, and now you're bringing up thread-safe collections. Can you explain the practical benefit of using concurrent hash map over, say, a regular hash map in a real-world application?
Definitely. Imagine a high-traffic web application. A regular hash map isn't safe for concurrent access, you know?
Right. What happens if multiple threads try to access it at the same time?
You get unpredictable results, data corruption, potential crashes. Concurrent hash map handles that safely.
So it's thread-safe?
Exactly. It uses internal mechanisms to guarantee that even during multiple writes and reads, it's consistent.
Can you give a specific example?
Sure. A website counter. 1,000 users hitting the counter simultaneously with a hash map could get a wildly incorrect result. Concurrent hash map guarantees the accuracy.
Interesting. What about these other concurrency tools like reentrant lock?
Those are more fine-grained. Reentrant lock lets you manage locks more explicitly, giving you more control.
More control? Can you elaborate on what that looks like?
You can acquire a lock in one part of your code and release it somewhere else. This is where you might outperform concurrent hash map.
How about situations where you need to manage multiple simultaneous events?
That's where semaphore and countdown latch come in. They manage access to shared resources with a controlled count. Countdown latch waits for multiple events before proceeding.
That's super helpful. I get it better now.
Choosing the right tool depends on your specific problem. If you need very fine-grained control, the reentrant lock is the way to go.
That makes perfect sense. A clear picture emerges.
In short, when in doubt, start with the ready-made, performant options like concurrent hash map, and escalate only if fine-grained control is necessary.
So the package java.util.concurrent is kind of the one-stop shop for this?
Absolutely. It provides the building blocks for reliable concurrent programming.
Thanks, Robert. This is super enlightening.
You're welcome.
So, Robert, you've been talking about writing clean code. This concurrent programming thing, it sounds like it's a big deal. What exactly makes it messy?
Yeah, Andrew. It's like juggling flaming torches. You've got multiple tasks going on at once, and if you're not careful, things can get chaotic. We have these concepts like bound resources, think limited database connections, that only so many threads can use at once.
So, if too many threads try to grab the same resource, it's like a traffic jam?
Exactly. Then you get mutual exclusion. Only one thread can access a resource at a time. If not, you risk corrupting the data.
But what's starvation? Sounds pretty serious.
Imagine a slow runner in a race. Fast threads constantly hog the resource, leaving the slow one waiting forever. It can happen unexpectedly.
Deadlock? Is that when everyone's waiting for each other?
Yup, a classic. Two threads need resources held by each other, getting stuck, unable to move forward.
And live lock?
Threads are like people bumping into each other, both trying to move but never getting anywhere. They keep trying, but they're all blocked. Sound familiar?
Wow, sounds tough. How do you know when one of these scenarios is happening?
You need to write very careful code to think about it. Lots of debugging. It's one of the biggest challenges in making fast and reliable code, you know.
So, knowing these potential issues is key to writing more robust concurrent code.
Absolutely. It's about understanding the why, not just the how. Next time, we'll dive into specific techniques.
Cool. So the main thing is to be aware of these dangers, especially when dealing with multiple processes competing for limited resources.
Right. Writing clean code in these environments means understanding these issues and knowing the tools for addressing them.
That's great insight. Thanks, Robert. Hey, Robert, thanks for joining us today. Let's talk about the producer-consumer pattern. It sounds pretty fundamental. Can you give us a quick overview?
Sure, Andrew. Imagine an assembly line. Producers make parts, and consumers assemble them. The queue is like the bin where parts are stored. The pattern coordinates this process efficiently.
So, producers put stuff into the queue, and consumers take it out?
Exactly. The key is managing access to the shared queue to prevent issues.
Like what kinds of issues?
Imagine two producers trying to add parts at the same time. The queue might get corrupted. Or maybe a consumer tries to pull a part when there isn't one. That's where signaling comes in.
Signaling?
Yeah, producers signal that the queue is not empty, and consumers signal that it's not full. This prevents waiting forever.
So, it's like a conversation?
Precisely. The queue is the message board, and the signals ensure things don't get missed or duplicated.
Got it. So, what are the benefits?
It's very elegant for concurrent programming, Andrew. You decouple the production and consumption phases. Producers can churn out work without blocking, and consumers can process it at their own pace. Also, it simplifies testing.
Makes sense. Any real-world examples?
Think of a web server. Producers' requests are handled asynchronously, while consumers' responders respond to them. High-performance systems rely heavily on this approach.
I see. It's about preventing bottlenecks and ensuring order.
That's right. The pattern is super useful for managing asynchronous operations.
Makes perfect sense, Robert. Thank you. Hey, Robert. Welcome to the show. Today we're diving into clean code, and something called the reader's-writer's problem popped up. Sounds fascinating.
It is. Imagine a database, tons of people reading data, but only a few updating it. Balancing that read/write access is tricky. Think of a website, high throughput for reading pages, but occasional updates are vital.
So, how do we avoid problems? Does prioritization impact everything?
Exactly. Prioritizing readers means fast response for all users, but could lead to stale data if updates are neglected. prioritizing writers may slow down the experience for readers.
So it's a trade-off?
Exactly, a delicate dance. A simple solution is blocking all readers while the writer updates, but that kills throughput.
Wait, can you give me a real-world example?
Sure, imagine a social media platform. Millions of users reading posts, but only a few writing new posts. The reader's writer's problem is super relevant here.
So how do you approach this balance?
It depends. You need to see the ratio of reads to writes in your app. This helps define an appropriate solution. Often, you'd use locks, but not necessarily a simple lock on the whole dataset.
Lock's interesting. Could you give me an example of how this works in a real-life context?
Sure, consider using a versioning system. This ensures that reads and writes don't clash.
Makes sense. So, are there different approaches for different situations?
Yes. There are many locking strategies, like read/write locks, or asynchronous programming patterns. You might need to use techniques like optimistic locking.
Okay. So, in simpler terms, clean code for concurrent programming relies heavily on understanding these trade-offs.
Exactly. Understanding how readers and writers interact is key to avoiding these conflicts in your code.
That makes complete sense, Robert. Thanks for explaining this so clearly.
You got it.
Great discussion. Thanks for sharing. Okay, Robert, so we've talked about using synchronized methods to avoid race conditions in our code. But what happens when we have multiple synchronized methods on a single object?
Exactly. That's where things get tricky. Imagine you've got a shared resource, like a bank account, and two synchronized methods, one to deposit and another to withdraw. You might have a bug if those methods aren't coordinated.
Whoa, so these aren't independent anymore.
That's right. If not handled correctly, dependencies between the methods can lead to weird behaviors, like lost updates or deadlocks, which can be difficult to track down.
So, what are the solutions then?
We have client-based, server-based, and adapted server approaches. Client-based means the client takes control of the locking, while server-based moves it inside.
Can you give an example?
Client-based locking handles the lock in the client. Say you have two methods, getBalance and withdraw. The client locks, then calls getBalance, then withdraw, then unlocks.
So, the client is managing the whole process?
Yes, but it can get complex and error-prone with more methods.
Interesting. Any pros and cons to each?
Server-based might be more robust if you have many methods that are inherently linked. The adapted approach comes into play when the server class cannot be modified.
So, what are the key trade-offs? What makes one better than another?
Performance and flexibility. Client-based might be faster for simple cases, but server-based is usually more efficient with lots of dependencies.
Makes sense.
Basically, think about the interaction between methods. If you don't carefully manage those interactions, you'll run into problems.
Thanks, Robert. I think I'm getting a better picture.
Glad to help. Let me know if you want to work through some examples.
Definitely. Rob, you were talking about multi-threading earlier. So, if I understand correctly, we need to be very careful about synchronization, right?
Absolutely, Andrew. Synchronization is crucial for multi-threading, but it's a double-edged sword. It's like locking a door. You need to lock the door to prevent multiple people from entering at once, but you don't want to keep it locked unnecessarily.
So, keep it small, you said?
Exactly. The smaller the synchronized section, the less chance of contention. Imagine a busy bank transaction. If you lock the entire account balance while processing a withdrawal, that locks everything up, creating a bottleneck.
But how small is small?
That's a great question. There's no magic number. You need to analyze your code, identify what parts absolutely require exclusive access, and keep those blocks as limited as possible. Think about the actual operations you need to perform atomically.
So, if I understand you correctly, it's about minimizing the amount of time that critical sections of code are locked?
Precisely. The goal is to minimize contention by synchronizing only the minimum amount of code necessary. This directly impacts performance because locks introduce overhead.
Can you give me a practical example?
Sure. Imagine two threads updating the same inventory count. A large synchronized block that locks the entire inventory would slow down the whole process. You could just synchronize only the increment operation.
So, we can identify that increment is the critical operation?
Correct. That's exactly where you need the lock, because you want to avoid race conditions.
Ah, so if I understand this correctly, instead of synchronizing the whole operation, we should only sync the part of the code where we might have problems with concurrent access.
Exactly. Well thought out, Andrew.
Thanks. This helps a lot. So, how do we actually detect when we're doing too much locking?
Tools and profiling can help you identify performance bottlenecks. You can also look for places where you're unnecessarily extending synchronization to sections that aren't actually critical. Sometimes, careful use of atomic operations can avoid synchronization altogether.
Atomic operations?
Yes. Some operations are designed to be atomic, cannot be interrupted, which can help eliminate the need for full locks entirely.
That's a very helpful insight.
You got it. It's all about that delicate balance between protection and performance.
Thanks, Rob. That was really clear. Hey, Robert, we're diving into the tricky world of graceful shutdowns today. You've been working with concurrent systems for ages. It seems like a simple concept, but writing the code for it, well, that's a whole other story.
Yeah, Andrew. Shutting down a system gracefully is often overlooked. It's much harder than getting the core functionality to work.
So, what are the typical pitfalls in this area?
Deadlocks are a big one. Imagine a parent thread waiting for all its children to finish. But if one of those kids is stuck in an endless loop or waiting on something, the parent's just frozen, never shutting down.
Whoa, that's a real problem. And the producer/consumer example you mentioned.
Exactly. The producer might get the shutdown signal and immediately quit. But the consumer might still be processing data the producer sent, unable to get the shutdown signal. It's like a one-way street. The producer can't see the consumer anymore, but the consumer is stuck.
That's like having a party, and one person leaves before the rest finish their drinks. You're stuck.
Absolutely. It highlights why careful design is key. We need to think about those interdependencies.
So, how do we plan for it? Any strategies or techniques?
Well, one is explicit shutdown signals. You know, a way for the parent to signal its children to wrap up. Another method is timeouts or periodic checks for completion.
Explicit shutdown signals sound critical. But how do you manage these in different programming languages?
That varies, Andrew. Sometimes languages provide built-in mechanisms for these signals. Sometimes you've got to design your own, using interrupts, mutexes, or semaphores.
So, it's not just about coding. It's about understanding the intricate ways those parts of a program interact?
Exactly. Understanding how threads and processes communicate is fundamental.
I get it. This isn't just a code issue. It's a system architecture issue.
It is. You really have to think ahead about how your system will interact during the shutdown process.
Wow, this is a much deeper rabbit hole than I thought. Thanks, Robert.
Glad to help. Just remember, graceful shutdowns are a critical, but often overlooked part of building robust systems.
Hey, Robert, so we've been talking about writing clean code, but what about when you have multiple threads working at the same time? How does that affect testing?
That's a huge difference, Andrew. Single-threaded code, you can often test it thoroughly. But threads, well, things get tricky.
Tricky how?
Imagine two people trying to update the same bank account balance. If they try at the same time, you get unpredictable results.
So, testing is harder?
Significantly. You can have code that looks perfect in isolation, but when you have two threads acting on shared data, errors can pop up surprisingly.
So what's the solution?
You need to think differently. Writing tests that cover every possible interaction is often impossible.
So how do you handle these mysterious issues that pop up?
Treat them seriously. Spurious failures are your friend. Run your tests with different configurations. And don't ignore them.
But how do you know if a test failure is from threading or something else?
Start by getting your non-threaded code working correctly. Then make your threaded code pluggable. This lets you swap in different threading strategies for testing.
Pluggable?
Yes, like Lego bricks. You can swap in different threads or thread pools to test different scenarios.
Ah, so you're looking for a pattern of failures?
Exactly. Plus, run tests under different loads. Many problems show up under higher loads. Also, on different platforms. You might be surprised how platform-specific a threading error can be.
Interesting. Any other tips?
Try to force failures by instrumenting the code.
So, instead of trying to prove correctness, we're trying to find problems?
Exactly. That's the practical approach. And it's not that different from other areas of programming. It's about risk mitigation.
Thanks, Robert. That's super helpful.
Glad to help, Andrew.
Hey, Robert. Thanks for joining us today. Concurrency is tricky, right? It's easy to get lost in the threads and forget about the actual logic.
Absolutely. Debugging race conditions can be maddening.
So, you're saying get the non-threaded code working first?
Precisely. Build your POJOs. That's, plain old Java objects.
Okay, but how do you decide what goes into a POJO?
Think about it. If a piece of code doesn't need to interact with threads directly, make it a POJO. If it has to update shared data, that's when you worry about thread safety.
So, like if I'm building a banking application, a transaction that just reads account balances.
Totally, that's a prime candidate for a POJO. Test it thoroughly outside the threading context.
Okay, but wait, what about performance? Don't I lose some efficiency by separating the concerns?
It's about trade-offs. Clean, debuggable code usually outweighs a little extra overhead in the long run. Imagine a system that works reliably. It's better in the long run.
So, you're saying keep the threads separate?
Not entirely separate, but minimize the interaction. You want those thread-related methods and functions in their own place.
Great. Is there a practical example?
Yeah, in a game, your game logic, like moving characters or updating scores, can often be a POJO. Thread management handles input and rendering, etc.
Got it. That makes sense. So, a well-defined POJO keeps it simple.
Exactly. Keep it testable and modular.
This is super helpful. Thanks, Robert.
You're welcome. Happy coding.
So, Robert, we're talking about making our threaded code super flexible, right? Like, able to handle different numbers of threads?
Yeah, Andrew, exactly. Adaptability is key. You want to be able to easily switch between using one thread, or maybe a whole bunch, without rewriting the core logic.
But how does that even work? Is it like using config files?
Exactly. You use interfaces and abstract classes. Imagine a task runner interface that defines a method for executing a task.
Okay, so we create a task runner?
Exactly. You'd have a real task runner for running tasks on your real system, and a test task runner that works with test doubles.
Test doubles? Like dummy systems?
Exactly. Mocks, stubs, fakes, different types for testing different scenarios.
So, you were saying we isolate the interaction with the system to different runners.
Exactly. That's the crucial point. You isolate that interaction. This separation helps in testing.
How can we control how these tasks run?
You can configure the test task runner to simulate different speeds, errors, or other behavior, so you can test many scenarios.
So it's not just one fixed way to run it?
No, you can run the tests for multiple iterations. How many runs will it take to break the code?
So, using different configurations, that's the key. Makes testing so much easier.
And the ability to vary the number of threads?
Exactly, crucial for load testing.
Absolutely. You can then observe the program's behavior under varying loads. It's crucial for scaling, robustness, and responsiveness.
That makes sense. So, you're saying making our code flexible is all about separating concerns?
Precisely. Decomposability is a key tool for creating robust, well-tested code.
Wow, that's quite a lot.
It's worth it for clean, maintainable code.
So, Rober, you're saying we need to be adaptable in our threading strategies? Like, let's not just pick a number and hope for the best?
Exactly. Finding the sweet spot for threads is often a process of trial and error, and it's often not a one-time thing. Imagine a network application. The load might change throughout the day.
Right, so you're suggesting dynamically adjusting thread count while the program is running?
Absolutely. You could have a system that monitors throughput and system usage and changes the number of threads accordingly. It's like a thermostat, adjusting based on temperature.
Is that always reliable, though? What if it makes things worse?
There are definite trade-offs. Self-tuning systems can be really powerful for applications with fluctuating loads, but sometimes a human's expertise is still needed to ensure optimization.
Makes sense. Manual adjustments, well, that's a lot of work.
It is, and often it depends on the characteristics of the workload.
What about different programming languages? Do they all handle tunable threads the same way?
Not exactly. There are varying degrees of support and built-in tools. For example, Java's thread pools are designed to be quite dynamic, making this easier.
So there's something in the toolkits.
Yeah, in most modern languages, libraries provide frameworks for managing threads, often with mechanisms for tuning or auto-adjustments.
Okay, so we're not just building code, we're building adaptable systems.
Exactly. It's about understanding that performance isn't just about algorithm complexity, it's about how well your software interacts with the machine itself.
That's fascinating. So, self-tuning is the solution?
Not always. It's a powerful tool, but it needs to be considered in the context of the task. A lot of tools are available to tune the number of threads.
So a bit of a balancing act?
Precisely. You need to know when to trust the system and when to intervene.
Thanks, Rober. That clears things up. Hey Robert, so you're saying we should avoid hand-coding yield calls for testing threading?
Yeah, Andrew, that's a really inefficient approach. It's akin to using a sledgehammer to crack a nut. You might hit the bug, but you're likely to introduce new problems and end up slowing things down in the process.
But sometimes it seems like a quick fix, especially when dealing with tricky threads.
Sometimes that initial impulse is really strong. It's like when you have a really nasty bug, you want the instant solution. But this often introduces fragility.
How do we go about creating these test harnesses you mentioned?
You want to decouple your thread management from your core logic. Think of it like having a separate conductor who orchestrates the musicians, your pojos. The conductor would dictate the tempo and different rhythmic structures for testing without altering the music itself.
So, like a music conductor for threads? Interesting.
Exactly. You have your pojos, your core logic, and then you have the test jig that controls the flow of thread interactions. That jig could simulate a high load, a low load.
So, is there a simple example of this separation?
Imagine a web server. The pojos are the actual handlers for incoming requests, but the test jig could be a scheduler that controls the number of active requests, the order of requests, and the times that threads sleep, potentially mimicking a real-world scenario.
So, it isolates the issue for testing without affecting the actual logic.
Precisely. You can then vary the conditions, the tempo if you like, and see how the pojos react in different scenarios.
Makes sense. Thanks for clarifying that. It's a very clean approach.
It's all about preventing those unintended consequences, the hidden bugs.
So, testing harnesses are the way to go?
Most definitely, when dealing with threads.
But, sometimes that debugging sledgehammer works.
There are always exceptions to any hard and fast rule. But these approaches are much more efficient, sustainable, and scalable in the long run.
Definitely. Thanks for the insight. Hey Robert, thanks for joining us today. We're diving into clean code, and this chunk talks about jiggling code for improved testing. Can you explain this concept?
Sure, Andrew. Jiggling is a way to introduce randomness into your code execution, essentially forcing different orderings of events to catch bugs that might not show up in traditional testing.
So, it's not just checking if something works, but how it works in different scenarios?
Exactly. Imagine a race condition, for example. You might not see it if all threads always run in the same order, but adding jiggling can potentially uncover those subtle errors.
That's interesting. How exactly does it work in practice?
Tools like aspect-oriented programming frameworks allow you to insert code snippets at specific points in your application's execution flow, potentially introducing delays or changing actions randomly.
So, you're adding, basically, code that changes the behavior based on randomness?
Yeah, kind of like a controlled chaos. You could have a method that might sleep, yield, or just proceed. You're essentially injecting different behaviors in different runs to see how the program responds under these variations.
That sounds a bit like fuzz testing, but with more specific intervention.
You've hit on a key difference, Andrew. Fuzz testing is broader in scope. Jiggling, in this case, is focused on making sure the application's execution path changes, potentially revealing race conditions or other time-sensitive issues.
So, this jiggling approach is more deliberate than fuzzing, designed to explore particular areas?
Precisely. It's targeted toward finding problems arising from the order of execution. It's a powerful technique for finding errors in complex multi-threaded applications.
Interesting. So, what's the drawback? Does it make the code more complicated?
Sure, it can add complexity. You need to implement the aspect code correctly, and it might increase development time in certain cases.
Great points. I can see the power and potential for a better set of test cases.
That's the key. It's about proactively searching for unexpected behaviors within the program, and if you use it well, potentially saving more time overall when compared to lengthy debugging.
Makes sense. Thanks, Robert.